Good to go. Perfect. Right. So I am going to take you through how to do PCA, and you're going to quickly appreciate how simple and straightforward dimensionality reduction, whether you're doing PCA or you're doing UMAP or you're doing TSNE, whichever the case, you're going to appreciate how straightforward and simple it is. It's honestly almost like a data pre-processing step. Actually, it is a data pre-processing step. It's what you do before you start your modeling steps. So we're going to go step by step. I could totally share this. Let me share this notebook as well, but we're going to work through it together to make some changes in it together. Sawa sawa. Let me just share it with you on the chat. And then the idea is that we're going to work, both of us, on it, and not one person.
Okay.
So you can open that notebook, and then so that it's easier for you to follow along, and it's also easier for you to contribute and give me more ideas on how to build on the same data set. Right? Just give me a thumbs up when when you've already opened the notebook in your IDE.
We're good, Mercy. I'm good.
All right, awesome. So great. So the week 1 project is a dimensionality reduction project where you have car sales data, right? So data about secondhand car sales, all right? So using this example, we're going to try and you're going to see where dimensionality actually gets introduced and how we can, counteract the issue of dimensionality. So I hope you always start with your virtual environment, right? You can see I have a folder called Advanced Machine Learning, and it's accompanying virtual environment where I do all things advanced machine learning 2. So those are the libraries I'm going to be working with. You have NumPy, your pandas, your matplotlib, etc. Now, when it comes to principal component analysis and TSNE, both of those are methods that are in scikit-learn. But for UMAP, you have to install UMAP yourself. So let me show you how to install UMAP TSNE. Yes. So for you, because you haven't installed UMAP before, UMAP is a library on its own. So let me just share this on our chat. You have to run this. So you'll run this in a cell. So pip install, you can run it on terminal, pip install, or if you want to run it in a cell, actually open terminal so that you get like more comfortable with running commands on terminal. Or if you prefer to just do everything on notebooks, remember to include the hiyo alama ya mshango inaitwangwa aje, the exclamation mark. So you can open your terminal, run pip install UMAP hyphen learn, because UMAP is a manifold learning method in its own library. But TSNE and PCA are all in scikit-learn. So you don't need to install scikit-learn unless you've started a new environment, which you do need to install scikit-learn. But if you're using the virtual environment for machine learning foundations, this should not be a problem, right?
Okay. It's
So,
downloading. It's downloading.
okay. Please update Jupyter. Install. Right. Let me know when it's done.
It's like 2/3 we're done. Still download. I don't know why it has gotten stuck at
It's
some
still
point. So let's
downloading.
continue.
My goodness. Okay.
Yeah.
All right.
That's package. It's sort of 9 or
Hello?
so it's good. It's good.
Okay, fine. So go ahead and load the data. So once you because now you have UMAP, you can go ahead and import the relevant libraries. You're good to go, and then load your data. You're good to go. So this is how our data is looking like. Why is there an echo?
Let me mute.
Okay. So like I said, the data is for secondhand cars, right? So you have company name, the type of the car it was, the variant. I wish I was a car like person. I'd know what variant means. The fuel type, whether it's petrol, diesel, or I think CNG is maybe gas. The tire condition, the make year, the owner type, the registration number, etc, etc, etc. So we are trying to predict the price of these secondhand cars based on the features such as registration certificate, accessories, service recorded, body color, etc, etc. Right? So I go straight into, I don't go deep into EDA. You can absolutely go deeper into EDA, but for the purposes of just learning dimensionality reduction, I didn't go into those deep specifics. But before, there's usually those how do I say it? There are data pre-processing steps that you cannot do without. So you cannot feed missingness to a machine learning model. So I check for missingness here, and I notice a couple of rows have missingness. For example, the variant has missingness. Accessories has missingness, and what else? It's just variant and accessories. Okay. All right. So there you go. Variant and accessories has missingness. Remember, in missingness, you check for uh goodness. You check for where the missing, you need to identify the missingness, and then you need to quantify the missingness. So if your missingness, as a rule of thumb, is if your missingness is more than half, imputation would be adding way too much bias to your model. So it's just better to drop uh, that column in its entirety, or use more advanced imputation methods. So there are other imputation methods where you actually fit a machine learning model in order to address that missingness. So here, this is a prime candidate for imputation because it's only missing 19%, 10%. So at least we can make the trade-off and make the argument that, okay, I have missingness, and if I do imputation, yes, I'll be adding some bias, but not too much bias in my data. Right. So variant is a mode, right? Variant is a categorical value, and so is accessories, right? So for variant, I choose to impute using mode, but there is a caveat with accessories because you can see accessories. What if the card didn't have accessories? Look at the type of values we have in the accessories column. We have music system, sunroof, and alloy wheels. What if the car doesn't have a music system? What if the car doesn't have a sunroof? Or what if the car doesn't have alloy wheels? So here I made again, data science, the art versus the science. So for me, my argument is the missingness in accessories is not necessarily missing data, but rather it just means that particular card doesn't have accessories. So instead of me imputing, I decided to replace or resolve that missingness by replacing the missing values with no accessories. So it becomes its own category. All right, because if you're imputing with mode, what if that card doesn't have those particular accessories? So the way I saw the data and the way I interpreted it, for me it worked best by if I assumed that the intended missingness, or the reason why it was missing, is not that the data is missing per se, but rather that card doesn't actually have accessories. So I create that unique category called no accessories, and all you need to do is just, instead of filling with mode, you actually replace it with another category. So there you have it. All right. And then I check for my missingness and we're good to go. I have addressed all missingness. For drop duplicates, I just go ahead and do a df.drop duplicates, and it drops any duplicates in my data. And then you can go ahead and do outliers. You can go ahead and do skewness. You can go ahead and do data distributions. But for the purposes of just illustrating dimensionality reduction techniques, I don't go into those. I don't go into that depth, but you absolutely can, and you absolutely should. So I go to feature engineering, and the one I'm extracting is the car age from the year of manufacture, right? So you have the year of manufacture, but I can say this car is 7 years old, 8 years old, 20 years old, etc. And that's what I choose to extract. So I create a function here that converts the current year and minuses it from today. All right, so you have the make year in your data. Then I take I extract the current year, and then the age of the car is the current year versus year of month dot year, what current year minus, oh yes, which is this, which will be the value I've gotten from my data frame. So I apply that to the car age I apply that to my column, and then I do my encoding, right? And I can encode my categorical features. I drop registration number because I don't feel like registration number is a unique identifier. There's nothing the model can learn from something like registration. I drop that, and then I perform one hot encoding. All right. And you can see initially what was my, I had 16 columns, right? So my data was not very high dimensional. But after I do my one hot encoding, look how many columns I now have. I have 1,109 columns. If I was to feed a machine learning 1,109 columns, even to do feature importance would be very, very difficult, right? It would be very, very difficult, because how am I looking at, even looking at 100 columns can be quite challenging. Now imagine looking at 1,000. I'd even argue looking of doing feature importance of over more than 30 columns, and I'm stretching 30, can be quite tedious, right? So now we have high dimensional data, which is data with a lot of features. And there we go. So you can see now I have some high dimensional data, and we are going to reduce. So the first, as you can see, dimensionality reduction actually comes before you do your modeling. That's why I'm calling it, it's almost like a pre-processing step. It's just that it relies, or it is based on some very advanced methods. So that's why we teach dimensionality reduction in machine learning too, despite it being technically a pre-processing step. So what we're going to do, the first thing is I separate my input variables and my target variable, which is what I've done here. And then I'm just now realizing I do not have a train test split. So let me just get that. Okay. So remember, let me ask you, Bridget, I spoke in machine learning foundations, I spoke about the concept of data leakage. Just what do you remember about data leakage? What is data leakage?
When you accidentally use data from, like, information from your training data leaks into the test set, such that there's like the model is learning info that should not be seen. Like, the model should not see info from the test set at all. It should just learn from the train set. Yeah.
Yes. And this info can also be in form of like underlying data distributions, underlying statistics. They should never cross paths. All right. So PCA, or no, let me not say PCA, dimensionality reduction is applied to both the train and test data. So you do dimensionality reduction of your input features, right? So it's kind of like scaling. You do dimensionality reduction of your input features. So in your input features, you have X test and X train. So you are going to fit transform your X train, but you're going to transform your X test. Pretty much exactly how we do our scaling. So that's exactly how you're going to do your dimensionality reduction in order to avoid data leakage, right? So you split your data like so. I've split my data, so I have 2,000 on the train, on X train, a really good split, 1,000 on my X test, 500 on Y train, etc. Okay, so the first thing I do is PCA is also very, very, it's still, how do I say it? Dimensionality reduction are distance based. You'll see in TSNE, we were using distances. We were taking the Euclidean distance, right? So it's the distance between data point 1 and data point 2 in the feature space. And then we use we use a normal distribution to convert these distances into similarity probabilities, right? And then we say now we're using Kullback-Leibler divergence to try and match um, the similarity distribution in the high dimensional feature space to the similarity distribution in the low dimensional feature space. My point being, majority of dimensionality reductions, or at least let me say PCA, UMAP, and TSNE, are distance based. They are in somewhere in their computation, they rely on the distance between data point 1 and data point 2. For this exact reason, you feed scaled data. You have to scale your data before you do your dimensionality reduction. So keep that in mind. You're going to split your data. So your typical workflow when it comes to dimensionality reduction will be, of course, handle your missingness, check for outliers, because the outlier will still determine the scaling technique you're going to use. Split your data, scale your data. Split your data, scale your data, then apply dimensionality reduction. So here we go. Just lose this. I do have an extra one. It doesn't matter for me. And there you go. So now we have our X train and our X test. They are in the right format. They are scaled, which then that is what we're going to feed to our PCA, TSNE, and UMAP. Now, here I need to fix this. It's going to take the exact form of this. So PCA. So I'm going to just call this train. So train PCA. And then I'm going to say X test PCA. And then X train PCA and X. I hope you're following and changing on your side as well. Now, this is how you do PCA. So PCA comes from the library, of course, scikit-learn, and it comes from the group of methods in decomposition. So this is how you import PCA, and you import it as PCA. Now, you can do PCA in two ways. You can either do it this way, which is, remember, you're going to, just like how we do our machine learning, where you create an instance of a model, right? You also, in this case, we're creating an instance of a PCA model. You can think, but the PCA technically is an algorithm. Let me call all of them algorithms. So we are creating an instance of a PCA algorithm. There are two ways you can create this instance. The first one is, you'll say PCA, so you'll create this variable that holds the algorithm, that holds this instance. So PCA is equals to PCA, which is the method, into bracket 0.95. So this 0.95, just write a comment there, it refers to the explained variance. Okay, so what is explained variance? Explained variance is, we said, each principal component, there's an amount of information it has captured about the original data set. So explained variance is the value given to, it refers to this information that each PCA has captured from the original data. So when I say PCA into bracket 0.95, you are telling scikit-learn, I want you to create the number of PCAs that is going to give me a cumulative explained variance of 0.95. So whether that is 25 PCAs, 2 PCAs, 3 PCAs, 4 PCAs, 10 PCAs, 100 PCAs, you create the number of of principal components that will give me a cumulative explained variance of 0.95. Remember, Bridget, we said last week that principal component analysis, it creates principal components, and principal components are axes. And it's by default, it's going to create principal components equivalent to the number of features. You see, how many features do we have? We have 1109. So when you create a PCA instance, it's going to create 1109 principal components. Principal component is an axis. Principal component is not data points. So it's going to create 1109 axes, which is not helpful. That's why we use something, that's why we're using this cumulative explained variance. So if 10 principal components is what captures the majority of information in my data, it will only create 10. If it is 2, it will only create 2. Now, that's method 1 of how to create, or how to create an instance, or how to apply PCA. The other method is this, where you actually explicitly define the number of principal components you want created. So you'll still create a variable called PCA. You'll still use the method called PCA in caps, and then n components. You're going to define a hyperparameter called n components. So this n components refers to how many principal components do you want the PCA method to create. Do you want 2? Do you want 20? Do you want blah, blah, blah? It's absolutely up to you. Now, the first method, the one I've highlighted, where you explicitly define the number of principal components you want to be created, you'll need a lot of trial and error, but it's not bad because you already have the script plot, which makes it very easy to interpret. The second one, which is defining the explained variance, which is 0.95, it's usually good, but sometimes the explained variance can result in, it would mean it needs to create a lot of principal components. So it's absolutely up to you. My job is to teach you the various ways you can achieve the same thing. So I'm just going to use my kawaida. I'm just going to use the method where you explicitly define that you tell PCA create the number of components equivalent that will give me a cumulative explained variance of 0.95. So let's see how many principal components it ends up making. So it ends up making 148. So tumeshuka from 1109 to, where am I? 248. I still kind of feel 148 is a lot of features, but let's proceed. No worries. But let me show you the other method as well, so you can appreciate the differences. As you can see, when after I have explicitly said 20 after I've explicitly said 20 components, it will go ahead and print 20 components. Let me just do this. There you go. Let's see. It's going to create 24 each. So let's see how these 20 components look like. So remember, I showed you the mathematical computation of principal component analysis. And mathematically, I told you that the mathematical computation behind principal component analysis is a computation called eigen decomposition. In this eigen decomposition, this computation outputs two things. It outputs what we call an eigenvector, and it outputs what we call an eigenvalue. So the eigenvector is the actual principal component. And remember, a principal component is an axis. So a vector is something that has magnitude and direction. And then the eigenvalue is now the explained variance of each vector, the explained variance of each principal component. So I can pull those. You can extract the explained variance from your PCA, right? So whatever name you give this variable, you can pull it. You can just say dot explained variance ratio, right? So this is the formula. And then from that explained variance, you can also extract from that same PCA variable, you can also extract the eigenvalues, right? Now, a scree plot, we said, a scree plot is basically it's basically a visualization. It can be a line graph, you can do a bar plot, whatever your style is. It's basically a plot of the principal components versus their explained variants. Okay, and the whole point is I want to get I want to optimize for the number of principal components that I should use, right? And you pretty much pick the number of the number of principal components that give you like the highest, what's it called? It gives you the highest cumulative explained variance, right? So at 20, right? Actually here I think a bar plot would be best. Let's see. Let me see if it would give me an error. Let's see. All right, let's see how to plot a bar plot. Remind me how to plot a bar plot with Matplotlib. Bar plot with Matplotlib. I actually do it here. Okay. So the other alternative, actually the easiest way to interpret this is usually just do a bar plot, okay? Because the whole point is to get cumulatively how many principal components will get me to the desired cumulative explained variance. Like I said, the ideal is 0.95. If you can reduce your high dimensional data to principal components that still retain 95% of the information in your original data, you're doing pretty well. But in this case, you can see the number of principal components that achieves this cumulative explained variance is still quite high. It's still 148 values. So you either reduce your standard, which maybe you say, okay, I just want I want to maintain at least 80% of my data and see how many principal components that amounts to, or you still proceed with 148 because 148 is still objectively better than 1109. So this is what you need to plot to optimize for the number of principal components. If you're using PCA, to optimize for the number of principal components, you need to plot a bar plot or a scree plot of the explained variance for each principal component. So principal component 1 explains 5%. As you can see, it's explaining very little, right? So you can even see here, right? From the PCA object that we just created, I can still extract the explained variance ratio, right? And then multiply by 100 so that I'm not dealing with 0.5. So as you can see, principal component 1 only explains 5%. Principal component 2, 5%. Principal component 3, like so, like so. By the time you get to principal component 1, you're only explaining 1%. So cumulatively, this is 5 plus 5, which is 10, plus 4, which is 14, plus 3, which is 17, plus 3, which is 20, 23, 26, 29, 31, 34, 37, 37, this is 37 plus 3, 40, 42, 41, 43, 44, 45, 46, 47, 48. You can see by the time you're getting to 20 principal components, you're not even explaining half of your PCA has not even been able to capture half of the information in your original data. Right now, imagine how many principal components. That's why it looks like we need almost 100, more than 100 principal components to actually be able to explain above of 95% of our cumulative. So that's how you interpret this. Okay, you'll get your explained variance and what. So explained variance, you can think of them as the eigen values of each principal component. And we want to look at the cumulatively, the first two principal components, how much do they explain, this the first 100, the first 10, etc, etc. Okay, now right off the bat, when you look at your data, so another thing with principal component analysis, which is very important for your EDA, is you're going to check for linearity in your data. So you're going to do your pair plot, and from that, it's going to be able to kind of give you a hint of whether I should use non-linear PCA, I should use PCA, which is a linear dimensionality reduction technique, or I should use something like TSNE or UMAP, which can be used for both linear and non-linear data. So right off the bat, the fact that we are performing very poorly, or we need so many principal components, which is still high dimensional data, in order to explain or get a good explained variance ratio, that tells us right off the bat that probably our data is not as linear as we think. So you explore nonlinear dimensionality reduction technique. The first one being, we can now do kernel PCA. All right, and kernel PCA is set up like this. So let's do this, and we can close this. Let me get train XPCA. Let's see what this gives us. Not so bad. As you can see, when we apply a nonlinear dimensionality reduction, we absolutely get way better results. So let me copy this and see what that gives us. Right. Let me see. Please feel free to copy as well. We need to extract these data first. Are you lost?
No, just finishing up on that part.
Okay.
Yeah.
Nataka KPCA. It says KPCA. Let me see. It's saying it doesn't have that attribute. Let me just get something again. Okay, so that one. So we have the eigenvalues. Mm. Mm-hmm. Okay. All right. So I have learned from documentation that kernel principal component analysis doesn't have a specific value called explained variance ratio, the same way that PCA does. All right. So kernel PCA would need to work backwards to compute the explained variance ratio ourselves. So let me do this. PCA explained variance ratio. Okay, let me call this KPC. KPCA, KPCA eigenvalues, yes. KPCA explained variance ratio. So I've extracted it here. KPCA explained variance. KPCA. Oh, yes, I see. KPCA explained variance ratio. Let's go. There you go. As you can see, the explained variance ratio for one is 14. This one is around 13. So let's say 14 plus 14, that's 28. This one is around 10, we're at 38. This one is around 9, so 38 plus 9, da 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 da. So by the time we even get to 10, our cumulative explained ratio is actually pretty good. It's actually pretty good. Let me see if there's a way I can print this. So print. Yeah, there you go. So let me print times 100 here. So we have 13 plus 13, that's 26. 36 plus 9, 48. 36 plus 9 is 48. No, 36 plus 9 is, yeah, 48. 48 plus 9. As you can see, even by the time we get to the fifth principal component, we've already explained more than half of the information of the kernel PCA has managed to already capture more than half of the information in the original data set. So even if we were to add, at least until like 20 principal components, I think we could totally get away with, we could totally get to 95%. All right. Any questions when it comes to kernel PCA? We've done the same thing, but we've done a little bit of workaround. So the bar plot is the same. It's still a bar plot of the principal components on the x-axis and the explained variance, and then you always look for cumulative. So let me even You're always looking for the cumulative explained variance. Bridget, you're free to ask questions.
No, I think it has made sense. At least so far we're good.
Hello.
Hello?
Hello. Now I can hear you.
Oh, I was saying, I think I've understood, at least today. It has made sense from the last time that we just discussed it, at least in theory. No, today is okay.
All right. So now let us do something on TSNE. Right? Let's try and apply TSNE. Let's see. Okay. So instead of, let me see, canal PCA, ratio, blah, 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 modeling. I didn't do TSNE anywhere. Okay. Let's do TSNE together. I'm just gonna take this. Feel free to check documentation as well. I was preparing this just before class. So it should, but the only difference should honestly be in how you create the dimensionality reduction algorithm. So in one, you're creating an instance or you're creating an object of a PCA algorithm. In this one, you're creating a TSNE object. So let's do that. So X TSNE, let me say X train TSNE and X test TSNE. And then we can do X. So we do a print of X string, yeah. X test TSNE. We apply that and see. Yeah, TSNE takes a little bit of time. What is the issue? TSNE X test. TSNE has no object transform. So you want to tell me TSNE you apply on both? I find that hard to believe. Let me just get something done. Reduce fast features of high dimensional components from the let me see how to apply TSNE. Scikit-learn, scikit-learn, scikit-learn. Again, I'm literally in the scikit-learn documentation, seeing why it's not kernel PCA. Where are examples? Spectral, locally isomap. For in combination, C, approximate near neighbors. So I'm seeing in the documentation, it looks like they don't put fit. So they don't do this, right? They don't do transform. So it looks like TSNE, you kind of have to transform the entire data set. So you, instead of feeding it X train and X test, you actually feed X. Stick on and pattern. So we're not going to do a difference of fit transform and transform. We're just going to do X. So this can become that. Interesting,
Okay.
interesting. Wait, let me confirm something. Let me confirm. Are you checking documentation? Are you checking?
No, but I can check.
Check documentation. We see this thing. Yeah, interesting. I'm very curious how it handles the issue of data leakage. Okay. Understood. So we do not, yeah, TSNE can be applied to, TSNE can totally be applied to your entire test and train data set, because TSNE is only, it learns topology, right? So TSNE and UMAP, or all manifold learning methods, they learn topology. They literally learn shape. If topology is like a huge word, they just learn what is the shape of data in the high dimensional space, and can I replicate that shape in the low dimensional space. So they're not learning statistics or data distributions, not like in the way PCA is. All right. So manifold learning methods, it doesn't have, you're not running the risk of um data leakage. So when it comes to manifold learning, you can absolutely do your dimensionality reduction first, and then you can do your train test split later. So let's try and follow um, that same, you know, let's try and follow that same idea. So we have X, I'm just going to call it X, then TSNE X dot transform, and then let me see something. Oh, goodness. Let's see, just form, and then so X TSNE dot transform, and then we're gonna print that and see how that works. So yeah, manifold learning, it's purely learning shapes. It's not learning any statistics or data distributions, or doing those computations that could lead to data leakage. All right. As you can see, TSNE has been able it has transformed your data into two principal components, which is very, very impressive. Now, when you do TSNE with let me see, when you do TSNE with what's the word I'm looking for? When you do TSNE with categorical, in a classification task, it becomes very easy to like do a visualization and see how well your TSNE has been able to capture the inherent structure in your data. But that visualization in regression looks a little tricky, but let's try and do so. So here I think it need it to one TSNE. This made sense. First dimension, second dimension. Let me see. The hue is the target. If we lose this, we lose. Let me see something. Just give me a sec. Mm. Mhm. So yeah, it's very difficult to the plot the topology in a regression task. So you pretty much just use TSNE, and now you'll use this. So now this becomes your X. So this becomes your X. This becomes your input variable, and then you're going to do a train test split on X TSNE. All right. So when you're doing your train test split, you're splitting this, and the same can be said for UMAP, right? All you need to do is this. All right. Mhm. See how it reduces them. It is the on no seed for parallelism. Yeah, UMAP is very heavy. All right. So note that you PCA you have to follow like the rules of preventing data leakage, but any manifold learning technique doesn't suffer from the same issue with PCA, because it's not learning statistics, it's just learning shape, and it figures out the shape in high dimensions and then tries to replicate that same shape in lower dimensions. So for here, you can see it's been able to reduce it to 2 dimensions. Here it's also able to reduce it to 2 dimensions. Now, how do you then decide which one is best for you? Of course, there's the issue of linearity. So if your data is linear, you use PCA. If your data is, you actually use PCA, TSNE, or UMAP, because manifold learning can be used for both nonlinear or linear data, but they are specifically really good for nonlinear data. Now, after you've sorted that, then how do I know, like, how do I know TSNE is good and UMAP is good? Because technically they've both what's it called? They've both reduced my data to 2 dimensions, right? We've already checked that box, which was dimensionality reduction. But how does it affect model performance? So typically what you'll do TSNE, UMAP, okay, you'll do PCA, and then you'll decide if PCA is, if you need to do it, if you need to now introduce like a nonlinear method. So if you see that applying a nonlinear method gives you better dimensionality reduction results, how then do you choose which one is better? So you'll choose between TSNE, UMAP, or kernel PCA by like applying that reduced data to like a very simple linear regression. Then choose the method that gives you the best performance on that linear regression. Then that's the method you proceed with, and now you test it on the multiple regression models. You do the hyperparameter tuning, and so on and so forth. That's pretty much it. Dimensionality reduction is usually considered like a pre-processing step. So there isn't a lot of back and forth here. It's just I have high dimensional data. Is it linear or not? How do I decide if it's linear or not? You're going to do a PCA, a simple PCA, look at the results, right? If your simple PCA gives you an explained, a reasonable and acceptable explained cumulative explained variance ratio. You don't even need to go further from there. You just continue with your simple linear PCA. If you feel like it's not giving you, it's still giving you very high dimensions, you do a nonlinear method, and then you pitch the nonlinear methods against each other using a very simple, whichever gives you a better performance using that simple linear regression, that's the one you choose. Any question? Any questions, Bridget?
For now, no.
Sawa. That's pretty much PCA. That's all of it. So tomorrow I'm going to
Hello?
tomorrow I have a webinar. We're hosting a Zindua. It's for. Can you hear me?
Yes. I had lost you a bit. Can you hear me?
Yes. Yes, now I can hear you. So tomorrow Zindua will be hosting a webinar on prompt engineering, because we're officially launching the month of June as our month of AI. So we have a couple of master classes in the pipeline, and as an inauguration of the coming master classes, we are hosting a free webinar on prompt engineering, which I'll be teaching. So what I'll do is I'll record a video of what clustering is and clustering algorithms, and then I'll just paste it on the LMS and you guys will watch a video. So you won't have class, but that the video will be available on the LMS, just like a typical class. And then we'll meet on Thursday. Is that okay?
Okay.
Hello? Perfect. So I am going to stop the recording there, and you guys